Ladies and gentlemen, please welcome the next speaker on stage, Aqsa Kasuar, Head of AI at Red Buffer and Google Developer Expert on Machine Learning.
All right, so hi everybody. So before we move on, I'd like to know with the raises of hands, how many of you were present at yesterday's session? Oh, that's a good turnout. That's a good turnout. So, all right, so for those who don't know me, I am a Google Developer Expert in machine learning. I currently work as a head of AI at Red Buffer, which is a services-based company. As part of Red Buffer and as part of AI at Red Buffer, what we do is we give AI services to company in Pakistan and to our clients in the US, Asia, Europe, etc. So moving on, what we'll be doing is diving a bit into AI consciousness. Just a slide bit, just to get everybody started on what AI is and how it actually works in images. So here we have an image where you can see some detections. So this is a common object detector. So you have a baseball glove being detected, a person being detected, and you have some probabilities associated with it. And similarly, this is another image where you can see the horse, the dog, the car, the person, and how all of this actually okay. So what happens when we actually pass an image through a convolutional neural network, right? Convolutional neural network is a network that's specialized for images, the way we have neural networks specialized for other tasks. So convolutional neural network, short for CNNs, is something that's specialized for images. You pass an image, and magically you're getting different kinds of classifications, detections out of that image, and you're able to train the model to learn those things. So how does that really happen intuitively, right? So what happens at the start of those models is that it's trying to detect the very simple things in images, the very simple things, the most simple of things in an image. So those simple of things in an image are things like the color, the different pixels of different colors, edges. So you can see that this is like a lot of different filters detecting different things. Some of them are detecting edges, some are detecting colors, but essentially, initially, what you're trying to do is you're trying to break that image down into edges and simpler things like colors. How this is important in machine learning is with this analogy, right? So when you want to draw a cycle, how do you really start, right? You draw with the simple things. You start off with the simple things. So you're drawing some circles, then you're combining those circles up to create a tire. Then you're adding some other rectangular lines, and you're combining all those simpler things up, and the simpler things here being the lines and the circles, the shapes, the edges, and you're combining those things up to actually create an object. So a tire is an object in itself, right? And then you're combining different objects to create another object, right? So the cycle in this case is an object that's created from tires and seats and handles and other things. So some of these things are common shapes, right? Like a circle, a rectangle, a line. But then some of these things are not common. Like, for example, the seat, that's a weird shape. It's not oval. It's not a rectangle. It's a different shape that's still made up of some simpler lines at certain angles, right? So in machine learning and in CNNs, this concept, this analogy is used. So when you pass an image into a CNN, the initial layers are actually trying to learn the different kinds of edges and colors that are present in that image. And as you move forward in the layers, what every layer is doing is combining those edges and those shapes to try to figure out which features correspond to which objects, and then which objects corresponds to which bigger objects, right? So this is a breakdown of a simple CNN and what it's doing at every layer. So for the start of the layers, you can see that it's detecting things like colors and contrasts. And as you move from layer 1 to layer 2 to layer 3, things combine up, and at the end, you have objects that are built, right? And when you look at it in a similar concept on how this is looking at a pixel level, then this is how it's looking at pixel levels, right? So for example, this one, the one that's third from in the last row, so that's humans being detected, right? And those are the pixels those are the features that the model picked up and said, okay, this looks like a human, with smaller features being picked up. Now breaking this down into another concept, because this concept is important for what we'll be talking about next, is neural style transfer. So neural style transfer is an algorithm that was introduced by Google a couple of years back, and the purpose of this algorithm was that you transfer the style of one image on another through AI, right? You have a model that takes two images, and you transfer the style of one onto another. So this is what the output would look like, right? When you have the previous image transferred onto Eiffel Tower. And this was the output from the model. So how does it actually start? How does the model do this? So the model starts by nothing but just random noise, right? So the model just has this image. You can call it an image, or you can call it random noise, or you can call it an image with just random pixels. The pixels don't mean anything, right? And what the model then does is that it takes contents, and content means objects, right? So the content of an image are like the main things, the objects. So for example, the door, the chair, that's content. And when you say style is basically the simpler features, the edges, the colors, everything that the lower layers are figuring out, and content is everything in the higher layers, right? So what this model does is, what it wants to do is, what it essentially needs to do to basically transfer style from one image to another is to basically take style from one and content from another image. And that's exactly what the model does. So it takes the content from one image, and it takes the style from another image. Now we know that the lower layers have lower features, right? Which are the edges, the colors. The higher layers have the higher features, which are basically the objects, right? So what this does is, you have content and style going into the noisy images. So the high-level features come from the content image, right? And the low-level features, the edges, the colors, everything, that's learned from the image on the right. And the content is learned from the image on the left. And the model combines those things up, and it creates what you see at the top, right? This. And this is another example of what this model does. So you have the style image, and you have the content image. So you can see that the final image preserves the content of the above image, right? So you still have the mosque, you still have the door, you still have the girl, but everything else is fed from the image that's down there, right? What's down here goes into the edges and the colors, right? So now we've been talking, there's some things that we've been saying, okay, lower layers, lower features, higher layers, higher features. And if you're training a model that has a lot of layers and it's outputting an image, so you're basically feeding in lower features from one image and higher features from another and combining those up, right? So you retain the higher features, and you embed the style. So this is another example, another one, and another one. So Snapchat actually has a filter that's based on neural style transfer. And to try this out, you can't try this out on, when you take that image right then, but when you go into your images that are already saved, and you want to edit one of those images, you can actually, you get something like this. So the lower filters, and when you press one of those, you will see that it doesn't happen instantly like it normally does with other filters in Instagram or Snapchat. It takes a little while, and that's because there's some neural style that's happening there. Okay, so we'll be diving next into GANs. So before we do with the raises of hands, how many of you have heard the word GANs before? A little higher. All right. So, okay, how many of you have heard that, AI is generating faces and it's generating, fake faces and new humans, etc.? How many of you have heard that? Right? Okay, so what's behind all that is GANs, right? So we're going to keep a lot of math out, but we're still going to try to understand what GANs basically do, and then what they have been doing for the past few years to bring AI where it currently is, right? So the GAN basically has two models, right? So a generator and a discriminator. How they work is that you have some paintings, you have two people, for example, right? And the job of one of them, let's say Sherlock, is to figure out whether the paintings are authentic or not, right? And the job of generator is basically to create paintings to fool Sherlock, right? So he wants to get better and better and better. The generator wants to get better and better at creating more realistic and paintings, so that you can just fool the discriminator that this is a real painting and it's not a fake painting. So and similarly, when you're creating fake faces, the same concept applies. You have a generator and you have a discriminator. So we're not going to dive into what a generator looks like or what a discriminator looks like, but they're two models that have certain tasks, right? So the discriminator has to figure out whether the image is fake or not, and the generator has to generate images, right? That's what the generator has to do. So now for the discriminator to be able to tell whether or not this is a real face or not, right? Whether this is a human or not, whether this looks like a person or not, the discriminator has to first know what faces look like, right? And that's where the real faces come in. So first and foremost, you teach the discriminator what faces look like, right? And right now, the generator hasn't stepped in, so it's just a discriminator, and we're training it, and we're making it learn what faces look like. And once that happens, then the generator steps in, and the generator starts off creating weird things, right? And it keeps doing something, and then the discriminator says, no, this is not a face. And it keeps trying. It has some feedback because of which it is able to improve. And so it starts to create better and better images and eventually start to fool the discriminator. GANs have been used in a lot of ways, and they have a lot of applications. You can also use GANs to create images of notes, currency, right? So the generator starts off creating something weird, right? And then the discriminator says, no, this is still fake. The discriminator detects is that fake. So the generator tries again, tries to create something better, and then better, and eventually it's able to fool the discriminator. So as the name suggests, generative GANs actually translate to generative adversarial network. So the word adversarial comes from the fact that you have two AI models that are fighting against each other. So that's the generator and the discriminator. So the discriminator wants to get better at figuring out what's fake and what's real, and the generator wants to be able to fool the discriminator. So they're like off against each other, and they're fighting against each other. So that's the word where adversarial comes in. So for the most simplistic, machine learning concept, the most simplistic, how the model actually is working, right? So you have some input, and you give it to a model. The model gives out some prediction, right? So it's the most simplistic, basic machine learning models. This is what they're doing. You have an input, you have a model, it gives a prediction. You compare that with an expected output, right? What you were actually expecting. And you use that to update the model, right? The most simple, most machine learning algorithms are following this one way or the other, right? So what happens in GANs, right? In GANs, you have a generator and a discriminator. The generator's job is to create fake samples, right? Fake samples that look real to the discriminator, but fake samples. The generator's job is to know what real samples look like, right? To be able to distinguish between fake and real samples. And the discriminator can do that for one domain, right? For one specific domain. For example, it's faces, or it's cats or dogs or something. So for now, it can only do this for one domain. So let's say we want to be able to create flowers, right? We want to create images of flowers. We want to generate images of flowers through a generator. So what we'll do initially is we'll show the discriminator a lot of flowers, right? So the discriminator would learn what a flower looks like. And then we'll show the discriminator some random non-flower images so that it knows what a flower doesn't look like, right? So it has both those things. So the domain is flowers. And once the discriminator knows what a flower looks like, then we start the generator's work. So the generator starts creating some flower images, and those start going into the discriminator, and the discriminator starts to give feedback, tell the discriminator whether the discriminator thought that it was fake or real, right? So both generator and discriminator at the end of the day are CNNs, right? They're convolutional neural networks. They are based on networks for images. And so the generator at the end of the day, when they're done fighting and the generator has come to a point where it's able to fool the discriminator to a certain extent, we can then use that generator to generate images of flowers. Okay, so until now, we know that we can use generators to create images, completely new images of flowers. But what if we want to do something like this? So you have images of zebra, and you want to just translate that, and you want images of horses. Or the other way around, right? You have a horse, and you want to convert that image to an image of a zebra. So how would you actually do that? So some things to remember before we move forward. So for a model, you always have some input-output pairs, right? There's some input and there's some output, and so you always have something like that in most models. The model is always trying to learn something, some task, whether it's generating images, whether it's detecting cat dog, it's doing something. There's always a loss function, right? The loss function is a way for the model to know how well it's performing, right? And to improve itself. And the function differs with the model based on what task the model is performing. So when we have multiple models in a network, that means that we also have multiple loss functions, and we also have multiple tasks, right? So how would we actually translate one image to another? So if you have input and output pairs, for example, these are satellite images, and I just want to convert them to Google Map images or similar to that, these are paired input outputs, right? So I have pairs of these images. So I have a satellite image. I will pass it through a network, an autoencoder, which is another specialized network. But we can pass it through this network, and we will get the translated image. Right? So since we have the pairs of images, we know what input should give what output. So what to do when you basically do not have pairs of images? For example, I want to be able to input images from one domain, for example, horses, and get equivalent of zebra images, right? I cannot have I cannot have a horse and a zebra always in the same pose, right? And say, okay, this is the input and this is the output. You can't have that. And that's a data that's very, very hard to collect, right? So these are some of the issues that you face when you are trying to do image translation from between two domains where you can't have pairs, right? In this case, for example, we can't have pairs for horses and zebras in the same layout. That's rare to find. So in this is where a new GAN was introduced. So that's called a cycle GAN. So what cycle GAN does is, so going back to what the generator and discriminator were doing, just revising that. So it generates images, the discriminator figures out whether it's real or fake, and then the discriminator is trained on the real images so that when it gets generated images, it's able to tell better which images are real and fake. And in all that process to fool the discriminator, the generator learns how to create and generate realistic images. So this is what a cycle GAN looks like, right? So now we don't have one generator, we actually have two generators here. It's because we want to be able to translate between images that don't have input-output pair. So how would this work? So the first generator would take the image of the horse and try to create the image of a zebra, try to convert that to a zebra image, right? But taking a step back, relating this to how the flower example, right? So the discriminator, to be able to figure out that whether an image is of a zebra or not, the discriminator needs to know what a zebra looks like, right? So what we'll start off with, we'll train the discriminator with a lot of zebra images. We'll tell it what a zebra looks like. And once the discriminator knows what a zebra looks like, then we'll plug in the generator. The generator would start converting the horse to the zebra, and the discriminator will start telling which is fake and which is real. So in all of this process, the generator should be able to learn how to translate a horse image to a zebra image, right? But there is one problem here. That one problem is that since the discriminator has no idea that we are trying to convert a horse to a zebra, it
is only concerned with whether the image is of a zebra or not. So the purpose of the generator's success is that you're always able to fool the discriminator. That's the ideal case for the generator. So what would happen here is that the generator would learn the first translation to zebra, and the first time that the generator sees that the discriminator is fooled, it will always create that same zebra image, right? Because that's the purpose of the generator. Irrespective of whatever input it's getting, it's always start creating just that one zebra image, because that's what the discriminator is concerned with for fooling. So this is where the second generator comes in. So the second generator, what it does is, it takes what's created by the first generator and tries to turn that back into the original horse. So this way, the first generator, if it is not translating, by translating I mean that if the horse is in this layout, the zebra should be in the same layout, right? So if the generator one is not translating, then the second generator would always, have a very high loss. It will always be failing. So for both the generators to pass, generator one must be able to create horse from zebra in that same layout, and the second generator must be able to convert that zebra back into that horse in the same layout, right? So this way, what eventually happens is that you can input the system any horse images, and it would output the corresponding zebra images. Why do we need to use this? Where this is used, where this can be used? It actually has a lot of applications, right? There's some research that's going on to be able to translate, for example, actors who have passed away, right? And to be able to take their images and translate them to actors in new images. So you could have movies with actors who are not alive anymore. So that's one research category that this opened up. So based on this cycle GAN, now what people wanted to do was, they wanted to be able to translate not just one horse to one zebra, but they wanted to be able to translate like a lot of other things to other domains, right? They didn't want it to be from one domain to the other. They wanted, okay, what to do. So what to do when I actually want to convert cat images, translate cat images to dog images, or I want to translate dog images to wildlife, or wildlife to cat. So based on what we studied, based on what we saw previously, with cycle GAN, you can only translate one domain to another. So one thing that I could do is that, okay, for cats to dogs, I can have a cycle GAN trained just for that. Then similarly for dog to cat, I could have another and another and another. And this would mean for as many domains I want to translate, I would have to have a separate model. So this is where star GAN came in. So star GAN said, okay, no, you don't need multiple generators. I am going to take just one generator, one discriminator, and you can convert images from any domain to any domain, right? Any number based on whoever's training that model, whatever domains they want conversions between, they can do that. So what initially happens is that horse images to zebra, that cycle GAN discriminator, and the cycle GAN discriminator gives a number of how confident it is that it belongs to a certain domain. But what changes in star GAN is that when you're inputting the image, you're also telling it, okay, which domain to translate to. So that's the number that's down there. So when you say 001, you're basically saying, okay, I want this cat image to be translated to wildlife image. So now the job this is what the generator then creates. And this then goes into the star-GAN discriminator. The discriminator then gives some probability of, how confident it is that this is now an image of a wildlife. So the generator now is responsible for a couple of things. Right? Since we're just using one generator for a lot of things, so it's now responsible for a lot of things. So one of the things that it's responsible for is, okay, I want to be able to fool the generator and create realistic images. Right? That's one thing, to be able to create realistic enough images. So you have the input, it goes to star-GAN, and that gives some output, right? So the generator would learn well to fool the discriminator that, this was a real image. But another thing that the generator now needs to learn is that it's generating and translating into the right domain. And for that, it uses the output. The discriminator also needs to be able to output what domain this is, right? And not just say, okay, whether this is real or fake, but to also be able to say what domain this is, whether this is wildlife or this is cat, right? So if a generator is taking a picture of a cat and converting that to a dog, but the purpose or the label assigned or the goal for that specific data sample was to be converted to wildlife, then the generator isn't really doing a good job, even if the discriminator says, okay, this is a real enough image. So you need both things. You need the discriminator to be able to say, okay, whether this is real or fake, and you need it to be able to say, okay, is it the right domain, right? And that's what the three numbers below tell us, right? So the upper one tells us whether it's real or fake, the probability, and the lower numbers, since we had three domains that we were translating to, the lower number gives probability for the three domains. So if we see that the highest one is 0.92. So that's the one, and it should be 001. So it's fairly close to what it should be. And then comes the last thing, where we said, okay, you're converting to the different domain. You're also, giving the right target. So you're converting. You're creating realistic image. You're also doing it in the right domain. But are you following the layout of the input image? Right? And in CycleGAN, you have another generator that's introduced, right, to convert the image back to the original. But what you do in this is that you use the same star-GAN generator, and you just change the domain. So in the first pass, you're actually saying, okay, convert this cat to wildlife. And then next time what you're doing is you're giving that generated image and saying, okay, convert it back to a cat. And then you can see whether or not it's the same as the input image that you gave. And all of this information is what is needed by the model to be able to understand, how well it's doing everything. And as long as the model has that feedback, as long as the model has some feedback that's going back into the model and telling whether or not it's performing right or wrong, the model is able to learn. Discriminator, on the other hand, has to differentiate between, okay, how realistic the image is and how fake the image is. And the interesting thing is that as the generator begins to perform better and better, the performance of the discriminator is actually going down, right? So for the generator to become really good, the discriminator has to become bad at performance, right? So with time, as the accuracy and the success of the generator increases, the accuracy and the success of the discriminator decreases. So it's a win-lose kind of a thing, right? So you have a winner in one pass, you have a loser in one pass, and that's how they continue to learn. The second purpose of the discriminator now is to be able to tell the right domain. So here you can see that, you had some images of the cats, and you converted those to dogs. The first one is very weird, but it's still something to see that, this is all done by AI and no human input. So following this came the style GAN. So remember that we talked that the style is all the lower features, right? The color, the edges, the shades of the images. So those concepts combined with GAN then led to style GAN, where you could style, you could translate images to different styles. So if you look at this image, the person on the top left and the girl on the top right. So you translated that person to her style. And you can say that, the colors of the hair, they have changed. The person is still wearing glasses though, right? So that's an object, but that's translated. And you can see that the hair are, more now. And similarly, and if you notice for all of the top images, right, translating to all of these styles on the left, you can see that the pose is the same. The pose of the image of the person remains the same. Their prominent features, they remain the same. But what changes? Hair color, skin color, these things are changing. So that's style GAN. So there's also another thing that picked up a lot of hype in AI, and that was image captioning. So now combining, all the text models that we have in machine learning, combining them to the vision models that we have. So you give an image, and it gives you some output of what's happening in that image, right? And the data for this is like, it's there on the internet. You have so many images with so many captions that you can build a model like this, right? And what this model would do is you would give it some image, and then it would give out a text of what's happening in that image. That's image captioning. So this is stable diffusion. This is what's being picked up, picking a lot of hype currently. It's, for those who are following, it's crazy. It's literally crazy. Like all of these images right here, they're all generated by AI. And all you had to do was just give one text input, just one sentence, one or two sentences, and you get images like this. So I was trying out stable diffusion, and I thought that, I'd try this out. So that's Tom Cruise sitting in Sri Lanka from Top Gun. Who are Top Gun fans? How many of you have seen Top Gun? That's very less people. Go watch it. It's a really good movie. So that's Tom Cruise from Top Gun sitting in Sri Lanka. And it literally took just 10 seconds for the model to generate this image. And then another interesting prompt. Prompt is basically the text that you give the model. So an insect robot preparing a delicious meal. So according to the model, this is what the model thinks, an insect preparing a meal would look like. So that's it on this presentation. I hope you got to learn some bit of, what's happening and how these things are happening, how, everything is moving towards what amazing things AI is doing, some very dangerous things as well. I personally think stable diffusion is as amazing and mind-boggling it is, it's a pretty dangerous tool as well. So I hope you got to learn something. I'll be around if you have any questions. And it was lovely meeting you all. Thank you.
That was an amazing session about AI. I would like to ask Aqsa Kasuar to be on stage. And I would like to call Keshan Sudhima, former GDG Sri Lanka lead, to come up on stage to give the token of appreciation. Thank you, Keshan Sudhimana.
Thank you, Keshan. So this is actually special because you gave this, and Keshan has been, you could say, a mentor before I became a GDE, and I first met him in Singapore. So thank you. Since you gave this, I was meant to, thank you publicly.